pruning is one of the most popular approaches to get rid of parts of the tree. So the most popular approach for that is called the alpha-beta pruning. Let's take an example with a two-ply game tree, just as follows. So this game is a two-ply in which we have max takes one turn and mean takes one turn. So we have the different actions of max given in this edges and the actions for mean given in these edges. So max is trying to maximize, again mean is trying to minimize. So we go all the way down the tree, so we reach 3, the mean will be 3. Then we find 12, the mean will not change. Then we find 8, the mean will not change. Just so the answer for this node here will be 3. For this one, we are going to do a similar fashion. So we're going to explore 2, and then 4, and then 6. The mean here will be 2. And then finally here, the mean will be 2. So at the end of the game, so we are going to have 3, 2, 2 for mean at this ply here. And then max will pick the maximum of these 3 values. It's going to be 3. The question here is whether we need to really explore all those nodes in order to find this value 3 that represent the maximum utility for max. And the answer is no. So for example, maybe this xy here are not really needed to calculate that the maximum is 3. So let's check it out. So we're going to check the minimax at the root. The minimax would be the maximum of the minimum value at 3, 12, 8, the minimum of 2xy, and the minimum of 14, 5, and 2. So the minimum of this minimum will be 3, this minimum will be 2. And this minimum here has to be less or equal than 2 because we have 2 in the list. So the minimum of 2xy, depending on xy, it's going to be 2 or less if x and y are less than 2. So this will bring us to replace actually the value of minimum 2xy by z, where z is less or equal than 2. This means that actually, given that we are calculating the maximum and then that the z is less or equal than 2, we won't need even to know what's z because we already have 3 that is maximum in this case. So the maximum is 3, and we didn't even need to look at x and y to decide that 3 is the maximum. So minimax decisions are independent of the values of x and y, which means that we can just not even explore them and just get rid of them by pruning. Based on this observation, let's devise the algorithm alpha-beta pruning that you might have guessed that it is actually a DFS algorithm. So just like minimax, the strategy is DFS. However, we need to carry parameters that are actually the alpha and beta of the algorithm from which the name is actually inspired. So we're going to use a DFS, but we're going to use 2 parameters that are 2 bounds. The alpha represents the largest value for max. This is the largest seen value for max among the children. In other words, it is the current lower bound on max's outcome. Beta is for mean. It is the lowest value of mean across the seen children, which is actually the current upper bound on the mean outcome. So we're going to carry this alpha beta along the search tree, and we're going to initialize them by putting alpha to minus infinity. This is like the worst case scenario. We want to find the largest value, and so far there is no largest value, so it's minus infinity. For beta, it's all the way around, so it's going to be plus infinity because we are trying to find the minimum, and for now we don't know yet what's the minimum. So the propagation is also very important. As we explore the search tree, we're going to send alpha and beta down the tree. So we're going to update alpha and beta values by propagating upward the values of terminal nodes. So how about the pruning? The pruning happens for any remaining branches whenever we have alpha bigger or equal than beta, which means that actually we're going to have alpha and beta starting from minus infinity plus infinity, right? And both of them will be moving. One is moving, alpha is going to go higher, beta is going to go smaller because beta, remember, mean is trying to minimize, max is trying to maximize. So whenever these 2 values will cross each other, it means that there is no hope for alpha, for mean, max to find a smaller value than alpha, and there is no hope likewise for mean to find a larger value than a beta. So whenever this happens, we are going to stop the search. It's not needed to search anymore. So alpha beta pruning could be also explained through these 2 diagrams. The left one is for max, the right one is for mean. So for max, if we have alpha as the best choice for max, then A down the tree, then max will simply avoid deploying or exploring that branch and prune it. Similarly, so it works similarly for mean. For mean, if we have a beta that is actually a best choice for mean, and there is another b that's actually a worst choice for mean, then mean will simply avoid exploring that branch here and prune it. So this is the idea for both max and mean doing the pruning based on their alpha and beta values. So the alpha-beta pruning algorithm is best if seen first through an example. So let's take again our 2-ply example. in which we have max playing first and then min playing second. So just remember stage 1, we're going to go through all the way deep in the tree. So we're going to pick 3, then pick 12, then go up to 8, and then the min will be, in this case, 3. And then we're going to go through the second min value C. We're going to explore 2, and we want to avoid exploring these 2 nodes here. And finally, we are going to go through the last node, explore 14, 5, and 2. So let's see for this specific example how these 2 nodes here are actually pruned from the search. So we start with the initial values for alpha and beta being -infinity for alpha and beta being +infinity. We're going to first send this down the tree as we do the search. So suppose we didn't do the search yet. So it's more convenient to write it this way, so as you could see the values as I run the algorithm. So we're going to send alpha and beta down. So alpha will be equal to -infinity and beta equal to +infinity. The min node here will explore its children. The first child is 3, then beta will change its mind. The value is no longer +infinity. We have a better min value for min, which will be in this case equal to 3. The second child explored will be 12 now. 12 is not better than 3 for min, and 8 is not better than 3 for min. So in this case, min declares that its minimum value based on its children is 3. And min will send back this 3 value to the max that calls the child its first child. So great. So we have 3 that's going back into max. What does max do with it? So remember, max is taking the maximum value among its children. So for the maximum value for alpha, we started with -infinity. So we have a better choice now. It's 3. So I'm going to change this into 3. We're going to start again over with the node C here. So in this case, we're going to send down the alpha equal 3 and beta equal +infinity in this case, because we have a better choice for alpha, as I said. The max value among these 3 children is so far 3. Then the min will start exploring its children. The children are starting with 2, so B will say, okay, so I found a smaller value than +infinity one more time, so I'm going to change my beta into 2. Which makes, in this case, we have warning, we have alpha bigger or equal than 3, the alpha beta crossed, which means that we are not going to find anything better than 3 in any subsequent children of the min node. So the 3 we found is really the better choice than any of these nodes here, because this will return 2 or less than 2 in this case. So I'm going to just cut these 2 nodes here and return the value of beta here. So we're going to send the 2 back. So remember, the max is doing the maximum of the children. So it has 3. It's C in 2, so it's keeping 3. All right. Last, it's going to again send, we are going to send down alpha equal 3 and beta equal +infinity to this node. The min node will explore its children. So in this case, we're going to have, so alpha is 3 and beta is +infinity. So when we explore the 14, the beta will update its, the min will update its beta. It's going to be 14. Afterwards, the beta sees 5. The next child is 5, so it's going to change the 14 to 5. And finally, change the 5 to 2. So I'm going to have min will update its beta to 2 and send the value back, which is 2. Okay? So again, here, max is taking the maximum of its children. It has 3, 2, and now it's C2. So it sees 2, so it's going to keep the value of 3. That's how actually max picks its value using the alpha beta strategy. So we end up with this configuration of minimax value for each of the nodes. We know that this one is 3. This is the final answer we had. This one is for sure 3. This one is less or equal than 2 because we didn't bother to explore this 2. We know that it is not going to be helping us in getting the maximum value for max. And this one is 2. So now here's the alpha beta pruning algorithm that looks very similar to, as you can see, to minimax algorithm. We have again a decision function that we use to call the maximize function, but this time we carry alpha and beta, -infinity and +infinity for the parameters. The maximize function we try to maximize for max, the minimize we try to minimize for min. With the exceptions that actually, as compared to minimax, what we are going to do is to add two things to each of the functions. One of them is to actually check for beta whether we need to cut or not, and update the alpha. And also we need to check similarly for the minimize function and check whether we should actually update the beta. So basically this is for whether we need to cut the search space, because we found actually alpha bigger than beta, which is the maximum utility that we find for this child. If the utility of this child is bigger than beta, then we need to cut. If the maximum utility is bigger than alpha, means that we found a new alpha, then we need to update alpha. So remember, alpha is updated only by max, and beta is only updated by the mean. So this is update beta, and this is also cut in case we have alpha bigger or equal than the minimum utility of the child. So if it happens, then we are going to skip this child and check the next child. So we're going to cut this branch for this child. So a similar algorithm, but we need again to do the bounce off between maximize and minimize, but we carry these alphas and we check them. And whenever alpha is bigger or equal than beta, this is the condition to prune for actually both maximize and minimize functions. So this was the alpha beta pruning strategy.